What can you guys tell me about your definition of chemistry? What is chemistry?
The study of elements and how they react to one another.
Anything else from our whiteboards?
I ended up getting the study / mixture of different elements, chemicals, and how well things go together.
So chemicals and how they go together. What else? While my first love has always been biology, I'm not going to lie to you. Without chemistry, not only can you not have biology, you can't have any of the other disciplines either. Chemistry seems like a very peculiar place to start biology, but the truth is, we have to, because remember one of the characteristics of life was that it had to obey the laws of chemistry and physics. It's hard to obey the laws of chemistry and physics if you don't know the laws of chemistry, right? So chemistry, the textbooky definition, the study of matter, and the changes matter undergoes. And you guys tried to tell me that with your definitions. If you said atoms and elements and chemicals, you were talking about matter. That's what you meant. It is always one of the things that just delights me. You always come to me with a strong understanding of what matter is. What is matter?
Something that takes up space.
Something that takes up space and has mass. We all know that one.
It's a matter of fact.
It is indeed. So it has mass and takes up space. There are very, very few things that don't fit under that definition. Heat, light, energy, radio waves, microwaves, none of those things count as matter. So how do we talk about them in biology? Because energy matters for biology. Well, remember we said that anything living has to obey the laws of chemistry and physics. So physics gets all that other stuff, the not matter stuff. But the matter stuff, the you-ness of you, that's chemistry. So that's why we start here. Anything with mass takes up space. What did you tell me an atom was as a class? What did you guys decide?
A basic component of matter that retains properties of elements.
That retains properties of elements?
Yes.
It's the smallest building block of matter.
None of you are going to accuse it of being a liar yet? Makes up everything, right? Isn't that always the definition I get? Every time I ask the question, what's an atom? It makes up everything. They do contain protons, neutrons, and electrons. We call those subatomic particles. Sub means below, so below the level of the atom. We have protons, neutrons, and electrons, and this is the first time of very, very, very many times I'm going to tell you how lazy chemists, biologists, and scientists in general are. We abbreviate like everything. So you'll notice I didn't write proton, neutron, and electron. I wrote P superscript plus, a lowercase p.
Some people call it efficient.
They're scientists, it's not word processors.
I like lazy.
They're scientists, not word processors.
Neutron, lowercase n, superscript of a 0. What's that tell me about the charge of a neutron? It's neutral. So these abbreviations, Mr. Dickey might be right. The efficiency of them also tells me about them. Electron, lowercase e, superscript of negative. Now this was one of the whiteboards I encouraged you to draw me a picture. I was like, hey, while you're doing these definitions, didn't I say draw if you can?
Yeah.
You are still squarely the Jimmy Neutron generation. And Jimmy Neutron taught you something like this. So if you were going to draw an atom, that's what you would draw for me. And I would tell you, you are patently wrong. Sorry. It's always like, it's wrong. Well, here's why we still draw this. This is why most people still draw it. What the atom actually looks like can't be drawn. It is absolutely correct in that there are two regions of the atom. So if you interpret this to mean there are two regions, there's a nucleus that's composed of protons and neutrons. And then there's an electron cloud. You're correct. And that's what Jimmy Neutron leads us to believe, right? There's that center area. Absolutely true. Made of protons and neutrons. And there's that outside area. It's made of electrons. But Jimmy Neutron leads us slightly astray here, where it leads us to believe that those electrons orbit on a fixed path. You think the electron is going around in a circle because there's a circle around it. And you think another one's going around in a different circle. You ever seen Hoodwinked, that movie with like red and, yeah, okay. You know that squirrel that drinks caffeine that could possibly be me? You know how you never really know where that squirrel is, and to understand it, you kind of have to slow it down? That's what an electron behaves like. It's constantly moving, all over the place, random pattern, unpredictable. That's an electron. Those of you who are like, I've never seen Hoodwinked. Where have you been? But that aside. If you've never seen it, you don't know what I'm talking about, I will have you picture a fan, like a box fan or a ceiling fan. When that ceiling fan or box fan is on high, are you ever able to definitively say where the fan blade is? JD's like, yeah, you can. This is how JD would do it. He'd stick his fingers in. Yeah? This is where I have to do the disclaimer, because the first time I did this with students, like, it makes total sense, but then I had one of them go home and stick their fingers in the fan. Do not go home and stick your fingers in the fan. So I have to do the disclaimer every time. But you can tell where the fan blade is for a single moment. The moment it strikes your fingers, and then it moves past your fingers. Same thing with an electron. If we know where it is, as soon as we say, it's right here, it's gone. Just like that fan, just like any propeller. So instead, we consider the electron cloud more accurately, much like that propeller. You know where the fan blade is or the propeller is because it's blurry, right? The area of blurriness is a high probability of encountering an electron. So if we were to accurately draw an atom, it would have that center nucleus of protons and neutrons, and the outside would be kind of like a blurry cloud. The more dense the blurry cloud is, the more likely it is to find an electron. How do we predict what those regions look like? Calculus. We use some pretty amazing math, which is why by the time you get to AP Chem, you have to have that pre-calc and calc under your belt, because we use that to predict the locations of electrons. Jimmy Neutron can't really make like a clever diagram of calculus. It doesn't make for good cartoon. So it's not, they didn't want you to not know, it's that it doesn't make a pretty little picture. What charge does the nucleus have if it's made up of protons and neutrons?
Positive.
And the electron cloud?
Negative.
Excellent. One of the comparisons we often do for the size or what an electron or what an atom would look like, take a shooter marble, you know, the big marble in the marble set, put it at the center of the 50-yard line. All the way out at where the track is where you would encounter electrons. Most of the rest of the atom is actually empty space. So kind of gives you a scale of what it would be like. And that electron isn't going to be anywhere like that shooter marble. It's going to be a lot smaller. Okay, cool. Can't be broken down into anything else. So what other substance do we know similar to that? Can't be broken down into anything else. An atom. So what else can you tell me about an element to distinguish between element and atom? Atoms make up elements? What else?
You should never trust them.
They do make up everything. An element's a specific type of atom, right? So we can classify all of the atoms that we encounter by counting one of their subatomic particles. The one that we look at is their protons. So any element is made up of the same number of protons. So its atom has the same number of protons. I'll give you an example. I do believe our friend sodium from the periodic table. That's one type of element. It has 11 protons in its nucleus, and it will always have 11 protons in its nucleus because the number of protons in an atom is its identity. That's how you know what element it is. So the number of protons is the identity of that particular element. Now, in an atom, the number of protons and the number of electrons are always going to be the same. So an atom of sodium has 11 protons in its nucleus and 11 electrons in its electron cloud. The number of protons in an element is its atomic number. The number of protons in an element is the atomic number. As chemists, we've assigned them this number basically as a way to keep track of it, to know who it is. It's much like when you were born, your parents are super happy, they did the whole like, yay, we just had a baby thing, they're in the hospital, they're celebrating, life is good. And the government officials come knocking. They visit you in your hospital room. And the reason they come knocking is not because they want your child's name. They want to be able to fill out the paperwork to give the child, the you that were born, a social security number. They don't really care about your name. The US government doesn't care about your name. They want your social security number. It's how they make sure you're a good law-abiding citizen and you pay your taxes. They do that because there's quite likely more than one of you out there. When I was at university, this is often my example I use. My college roommate, her name was Erin Smith. There were 6 other Erin Smiths at the University of Michigan when we were there. Not in the country, in our school population. 3 of them were Erin A. Smiths. So it was kind of generic, right? The university kept track of them by assigning them that social security number. So when we keep track of atoms and elements, we assign them that number, that identity, their atomic number, and that's how we keep track of them. It's much easier that way. Now there are 118 different elements. We put them in order on the periodic table by increasing atomic number. So if you ever look at that periodic table and you wonder what the numbers at the top are, it's the number of protons in the nucleus for each atom of that element. There are, I do believe, 20 or 22 elements you need to know for biology. So we're going to learn all of those, and I will give you that list, and you have a quiz on them on Monday. But I'm going to caution you as I give you this list, spelling counts. Rarely in your life Does spelling count? Because you have autocorrect. You don't get autocorrect here. In chemistry, we don't rely on autocorrect. You have to know how to spell it. Spelling's going to count. When we abbreviate elements, do so with 1 or 2 letter symbols. There are a few that are 3 letters, like unalquadium. That's got 3-letter symbol. I don't care if you know where unalquadium is. I don't care if you know what the abbreviation is. We're going to stick with the 1 and 2 letter ones. Here's what I want you to know, and ladies, unfortunately, I have to accuse you of this much more often than I accuse the gentlemen in the room of this. It is kind of a girl problem. Way back in the 1st grade, Mrs. Adamian gave us pieces of paper that looked like this. They had blue lines with pink lines down the center of the page, or down the center of the line, right? And when they gave you those lines, it was to help you, little you, figure out the scale of letters.
I hated this.
Well, guess what? It's coming back. Wow. I didn't know we were going to have like so much deep-seated emotion with like the dashed line. Because quite frankly, I look at this and there are fond memories. Because I remember when life was easy enough that all I had to worry about was making a letter the whole size or a halfway up. And that's all that was expected of me. Like, don't eat the paste and make the letters the right sizes. Like, that was good, right?
At my school, we had to put a pinky space in between each and every word.
I think we had to do that too. I think we did. So I'm going to warn you guys, ladies, I really hate to accuse you of this, but it is usually you who are guilty. When we abbreviate things, we're going to start with our friend sodium. When we abbreviate, the first letter of the element symbol is the full size of the text line. It is a capital letter. The second letter is a lowercase letter, and it takes up half the line. You're like, oh, 1st grade. Yes.
Yours is slightly smaller than the second half. F for you.
It is slightly smaller, because my N, I feel like, blended into the white line, so I didn't like it. It bothered me a little. But I caution you. And there are some of the artistic gentlemen in the room who will do this as well.
Hey.
That is not a lowercase a. No, you cannot do that. That is categorically, scientifically wrong. Nah, that's not right. Don't do it. He got me. At least there was somebody. That tends to happen an awful lot. As does, oh, I can't use the back button. Use this. I'll just. No! No!
No, it's not.
That is wrong. We can't do this. This is a lowercase n. Just because you made it gargantuan does not mean it's not a lowercase n.
Sounds like uppercase N's kind of look like that, because
Uppercase N, right?
You made the A.
If you find the need to reteach us this, then I'm starting to question the effectiveness of the school system.
I find the need to reteach this because I do actually have to mark answers wrong every time I do this. So I do this to make sure I leave a firm impression in your mind. Just like I'm going to harp on you about spelling, because last hour we had some pretty close to meltdowns because they're like, you mean spelling counts? Well, okay, Captain Attitude. Yes, spelling counts. Really? I mean, really. Usually I don't dock you out for spelling. I will correct you but I won't take off points for it. This is one of those rare instances where I have to.
Spelling makes